pretty well. Okay, so the slides we're going to be following along with, right, in Google Classroom are the same ones we had last time, standing waves and musical instruments. And I'm basically going to like slide 3 right now, although we'd already talked about slide 3 and 4. Slide 3 and 4 are really just like showing you the mathematical pattern that works for these devices. Whether it's a string or whether it's a tube, they're both called 2L devices because the mathematical pattern that exists depends on 2 times the length of the string or the tube. They're called 2L devices, okay? All right, well, what we want to do is see how this could play out with a musical instrument. So in the slides, I have an FFT graph that was created when somebody played an E note on their cello. I don't know how many years ago this was. This was some years back, but we had a student who brought in a cello, and basically she took the bow and like just pulled it across like one string, and she basically created an E note, and this graph was made. Now we got to spend a little time like reminding you about where these graphs came from. We've talked about FFT graphs before, so what I'm going to do is I'm going to make a couple FFT graphs for you again, with just random noises with my voice and with a musical instrument, so you can see like what we're trying to get out of this. An FFT graph, remember, it basically is displaying all of the frequencies that are being made by some device, and it's showing you their relative strengths. I know one of the things that people really struggle with when they're thinking about these graphs is understanding the language, so I want to like really make this clear. Down below, over here on the far side of the x-axis, right, this is like a frequency of 0. As I go to the right, I'm just seeing frequencies. Right here is a frequency of 2,000 hertz. That's a high frequency. I can't even come close to making a sound that sounds like that. It's like higher than that, right? Maybe during the lab in a couple of weeks, you guys are going to try to see if you can make a 2,000 hertz frequency. There are some people that can make some crazy high squeaks. It's amazing. That'll be part of the lab. It'll tell you, try to make like the highest sound you can make. We'll see what comes out of that. But really, I want you to just notice that what you're seeing displayed right here is that there was just a bunch of random frequencies being made. The loudest frequency is the tallest one. In this situation, that frequency right there was the loudest because it's the tallest. That was around, 200 hertz. What's cool about the software is that it tells you what the value of the loudest frequency is. It actually turns out it was 300 hertz. So when I just hit record with just some random background noise, I got 300 hertz, okay? All right, well then you remember I had done this where I tried to sing a note. All right, so here we go again. You guys get to be impressed with my awesome musical ability. He says tongue in cheek. All right, here we go. Ready? All right. So you can see this is not a bunch of random frequencies. I'm going to spread this out so we're not going all the way up to 5,000. We're going to make it to where we're only looking up to 2,000. So what we are seeing is all the frequencies that were being made from 0 to 2,000 hertz. And again, it's no longer random, right? Do you see that there's a frequency that's right here? Got to get my pen ready to write. Do you see that there's a frequency right here? There's a really strong frequency right there. There's a really strong frequency right there. There's another not so strong there, and one that's not so strong. And I don't know, there's one that's even kind of weak down there. Okay? Raise your hand if you can see how that fits a pattern of a 2L device. A couple of you do, right? Let's talk about why this fits a pattern of a 2L device. Remember, the mathematical rule was the frequency of any resonant frequency is equal to an integer number times the fundamental. The fundamental is the lowest frequency that can resonate on the object. When I say lowest, I mean closest to 0. I don't mean shortest. I mean the closest to 0 frequency. So, which one's the fundamental frequency on here? Let's say I labeled them. Let's say I labeled this A, B, C, D, E. Well, this would be a great multiple choice question. Which one is the fundamental frequency on that FFT graph?
Isn't it A?
A is, right? It's the one that's closest to 0. Which one's the third harmonic?
C.
C is. Can you see how? Can you see how this frequency, which is around 100, 200, I don't know, a little bit lower than 300. Let's call it 280. That's a 280 hertz frequency. This one is 2 times that. It's 560 hertz. This one is 3 times that. 3 times 280, 560, carry the 840. This one's 840 hertz. And you keep going. Can you see how that matches a 2L device pattern? Right? When I'm looking at FFT graphs, here's always what I do. I look at the gaps. I look at the spacing. If the spacing from 0 is even, it's a 2L device. I look at that space. I look at that space. I look at this space. I look at that space. It's even spacing. It's like steps, right? It's like when you walk down the steps, all the steps are the same height. It's a quantum idea. This is a quantum idea. Do you see it? 2L device, right? So hey, this is what this tells me right away. My voice operates like a 2L device. Hence the reason they're called vocal cords. All right. If I go back to the notes really quick, I'm gonna skip a couple slides and go out of order. There's a whole slide in our notes about how vocal cords work. Literally, they function like 2L devices. Like, I don't know, there's some like interesting graphics here, and there's all kinds of like really super interesting stuff that you can think about how your vocal cords operate like strings. You can make them tighter, and therefore you can make higher frequencies because of that. You can like change the shape of them, and so you can change the way things sound. Vocal cords are 2L devices, right? If you want to watch a really disturbing video clip sometime, click on this thing that says vocal cords while singing. We're not going to watch it right now because we don't have enough time, and I know everybody trying to watch this on video, it won't work very good. But literally what they did is they took some cameras and they shoved them up people's noses, and then they went like down into their vocal cavity, and then when they're singing, it like shows you what their vocal cords look like. It's gross. I'm just telling you. Now, don't do that right now because I want you to continue to learn. But vocal cords are 2L devices, all right? Well, then, now when you start to go back to this FFT graph that I supplied to you of a cello, you should be able to see that they're 2L devices, right? Now, what I'm going to do here is I'm going to circle all of the frequencies that would be considered resonant frequencies on this slide, okay? So the very first one that stands out is right here. That's the fundamental frequency. That's F1. The second frequency happens to be the loudest in this one. That's F2. And then there's F3, F4, F5, F6, F7, F8. There's a little F9, F10, F11, F12. A cello can actually have 12 resonant frequencies that are all playing at the same time. I don't know if you guys are familiar with what a cello is, but to me a cello has got to be like one of the nicest sounding musical instruments that there is. They always play cellos in like sad scenes in old Western movies, right? Like that's the cello. And it sounds so nice because it can play 12 resonant frequencies, right? What we try to do right here is provide to you what the standing wave looks like for each one of those harmonics. And these should be familiar pictures to you, right? This is the fourth harmonic right here because it's got 4 antinodes. That's happening on the string. Again, if you want to sometime, go look at these 2 video clips because they show the standing waves. What they did is they took slow motion video of, I think this one's a guitar string. They took a slow motion video of the guitar while it was resonating, and you can see all the waves. It's really cool. It's really cool. Okay. All right. Well, speaking of a guitar, let's go ahead and just do one of these live because I don't know, seeing it pre-made is one thing, but actually seeing it live is another. So I brought my guitar from home. I cannot play the guitar. My wife bought me a guitar. when I was like 30 years old or something like that, thinking that I was going to become this like dude that could play the guitar, and I couldn't learn how to play the guitar. I don't know. I just don't have a lot of musical ability. But it's good for physics, right? So what I'll do here is I'm going to collect this. Since I need like a person to help me collect, I'll have you do that so you can see the mouse, right? What I'll do is as soon as I pluck the string, you want to hit collect. All right, so here we go, everybody. I'm going to play the thickest string on the guitar right here when I do this. Ready? Here we go. Did it work or am I in your way? It worked. All right. So look, that definitely isn't as pretty as what we saw before. So what I need to do is maybe orient myself a little bit better and try to do this again. Here we go. Ready? That one's better. Okay. Still not probably as awesome as it could be, but better. All right, so let's spread it out so we can go from 0 to 800 hertz. You guys right now tell me, how many harmonics are you seeing resonating based on that graph?
I think 9. Probably more.
I could say 9. I mean 8. Like, are you going to count that one? I don't know. It's pretty weak, but I mean, you can see it's there, right? I'm going to circle them. Okay. Here's 1, 2, 3, 4, 5, 6, 7, maybe 8. Maybe 8. Somebody said 9. Were you thinking down there? I don't know. I go with, I'd say 8. Okay, fine, 8. Which one's the loudest? The second harmonic. The second harmonic is the loudest. It's the tallest. The software tells me what the value of the second harmonic is. The second harmonic is 158 hertz. My guitar must be out of tune because I think that's supposed to be 160. So my guitar is a little out of tune. No surprise. It's been sitting in my garage since COVID summer. I tried to sit in the garage and play during COVID. That didn't happen, right? So no surprise. Now math can help us figure out what the fundamental is. What's the value of the fundamental frequency using math? Around 80, right? Because if this is the fundamental times, if that's the fundamental times 2, then the fundamental is that divided by 2, right? You can see how this works. Simple enough. Okay, let's take that and go a further example. So I'm going to write this on the board just so I can remember what the numbers are. F2 is 158 hertz. Okay? And now what I'm going to do is I'm going to do an example on the TV. I would highly recommend that you guys maybe write this example down in your notes so you can use this as a sample later when you're trying to solve some problems. Okay? Okay, so I know that the frequency of the second harmonic on that string is 158 hertz. Okay? Let me take a look at my video and make sure that, you guys at home and the video should be able to see that well enough. Okay? I know that I plucked this string right here. I have a meter stick right here where I can measure what the length of that string is. Right? If I go from the top bar to the bottom bar and measure the length, that string's like 84 centimeters long. So I'm going to write down that capital L is 84 centimeters. That's the length of the string. Of course, we probably should convert that to meters real quick. 0.84 meters. From just those two numbers, I can figure out a lot of things. One of the things I can figure out is what's the wavelength of the wave of that wave. I can figure out the wavelength of the second harmonic because I know a relationship between wavelength and length of string, right? Hey, I wrote it up on the board, but also I want to make sure you guys are aware it's on the summary of physics equations. Okay, so that's why I put the summary of physics equations out on your table today so you could see that the 2L device equation is on there. If you look at waves and sound, right, you can see where the 2L device equation is right there in the bottom right-hand corner. the wavelength is related to 2L over N. L is 0.84 meters. N is 2, because I'm dealing with the second harmonic. The 2's cancel out. Hey, it turns out that that particular wave is the same as the length of the string, which is what happens when it's the second harmonic. So I know what the wavelength is. Now I could figure out the speed of the wave on the string. Okay, the speed of the wave on the string. What's the equation that you can use to find speed of waves if you know wavelength and frequency? It's wavelength times frequency. Here's the thing I want to really make a strong point of while I'm showing you this answer. Because I'm using the second harmonic wavelength, I've got to use the second harmonic frequency. You got to make sure you match up the numbers. So, I don't know, 0.84 meters times 158 hertz is, I ran out of room, .84 times 158. I get 132 meters per second. What's crazy to think is that when I pluck this string, that pluck moves to the right at a speed of 130 meters per second. I mean, it goes really fast, right? If I pluck this string, it goes faster. And the fact that it goes faster means the frequency that would resonate is a higher frequency. That's why it sounds like a higher pitch. If I did the FFT graph for this, we would expect to see harmonic frequencies that were higher in value. In fact, what I'll do here is just kind of show you that on my FFT graph that I have right here. If I plucked that string, I would anticipate that maybe that fundamental frequency would be right here. And then the next one would be like right here. And then the next one would be like right maybe here. I don't know how tall they'd be. I have no idea. I would have to like test to see their height. But where they are, I should be able to predict. Well, I feel like that's a great test question too. If it wasn't just going to be like a full multiple choice test, if there was going to be like a free response section, I would give you like a blank FFT, and I would say, here's where the fundamental is. You draw in the second and third harmonic. And you would just do that by trying to make the spacing even. Does that make sense? Okay, so musical instruments like this work as a 2L device. Of course, that makes sense because it's a stringed instrument. There are other musical instruments that are not stringed instruments. There are some musical instruments that are like pipes, open at both ends, right? I have a musical instrument right here that is a pipe open at both ends. How many of you guys were masters of the recorder when you were little? Maybe not masters. But... Hey, I was surprised this little like, they don't do this little like yarn thing anymore. Are you guys familiar with the yarn thing? So when my kids were in elementary school, which was some years back, I mean, I don't know, only 4 or 5 years before you guys, they would like get a different color yarn depending on which level they passed, right? So then they became like like different levels of ninja, right? So my son Luke must have been really good because he's got a bunch of different colors of yarn on here. All right, so look, here's the deal with this instrument. When I blow air through it, right? Wow. I'm making the air inside this thing resonate. I'm creating an antinode at the open end. And then I'm creating an antinode where all the holes are. So if you think about it, when I do this, I'm making like, well, there's an antinode. That's like probably like the 8th or 9th harmonic that I'm creating inside of there. That's why it's a high frequency. If I want to create the lowest frequency that I can possibly create, I got to cover up all the holes, right? And then I have to make sure that I blow the air very slowly. If I blow it too fast, I like make the speed higher, and by making the speed higher, I make the frequency higher. I don't want to do that. I want to make this the lowest frequency that I can possibly make. Let's get an FFT graph for that. So once I go like this, then hit collect, because I got to make sure I'm getting a good note. Oof. Not so good. Actually, just fine. Can you guys see the 2L device pattern? Hey, you heard it kind of squeak a bit on you, right? There's a little squeak that messed it up. But if you look at the prominent frequencies, can you see the 2L device pattern? Okay. Somebody describe to me how I would know to circle the fundamental frequency. What would I need to do to circle the fundamental frequency for this FFT graph? Which frequency should I circle?
The first one.
The first one. The first one starting from the left. In this particular situation, it's the tallest one. Right there. That's F1. It looks like it must be about 520 hertz. The second one, right there. The third one, right there. Why am I ignoring all the junk in between? Well, because it doesn't fall into that 2L device pattern. That's the little squeaks that I made that I didn't need to make. If we brought up like a professional recorder player up here and had them do it, theirs would have been perfect. Right? Who wants to volunteer for that? Anybody? Actually, I normally would, but we don't have enough time today. I'm sorry about that. But anyway, you guys see how that's showing a 2L device pattern? Yeah? We're going to do a quick example with this too. Okay? This time we're going to solve for something different. I'm going to use the value of the fundamental frequency on this one. The fundamental frequency on this one was 500, let's call it 528 hertz. Okay, that's the one I'm going to use for that example. Okay. So this is a pipe that's open at both ends. The fundamental frequency was 528 hertz. I'm making sound resonate inside that pipe. Sound has a speed that we know. On another day, we'll talk about like how we can figure out what the speed of sound is. But for today, just go ahead and take my word for it that the speed of sound is 343 meters per second in the room today. Okay? From that, I can figure out two things. I can figure out what's the wavelength of the wave that I'm creating, and what's the length of the pipe that I was just blowing air through. I can figure that out. Okay? The way I'm going to figure out wavelength is by using the 2L device equation. Wavelength is 2L over N. No, that doesn't work. I can't use that equation because I don't know the length. So I got to come up with some other way to find wavelength. Well, the wave speed equation helps me find wavelength because I know speed and frequency. I can take 343 meters per second and I can divide it by 528 hertz. And when I do that, I get 343 divided by 528, 0.6496 meters. I want to make sure you recognize I just found the wavelength of the first harmonic. Right? I found the wavelength of the first harmonic because I used the frequency of the first harmonic. Now I can find the length when I rearrange the 2L device equation. This is not rearranged for you on the summary of physics equations. So you'll want to maybe make sure you have that on your note card for the test on waves. But it's basically N over 2 times lambda. And in this case, I was playing the fundamental frequency, so N is 1. And lambda, I just found, was 0.6496 meters. So half of that. That says it's a 32 centimeter long pipe, or 0.32 meters. Now, I will tell you, when you look at this thing, it's not 32 centimeters long. It's probably close to that, but it's not 32 centimeters long. That's because when you're talking about pipes that are open at both ends, this is approximate. Do you guys remember when I talked to you about the tube, that the antinode wasn't right at the end, but it was a little bit farther outside? That's the same thing that's true here. The antinode is actually a little farther outside of the end. So this is an approximation when you do it with a 2L device, with a pipe. Does that make sense? Okay, cool. So if that was it, boy, we'd be all good. Now, some of you guys might have looked on the summary physics equations and noticed that there's another equation that has 4L over N instead. Well, that's because there are some devices, there are some things that act as what we call a 4L device. So let me show you those things, or that thing. This is a pretty rare thing, honestly. There's not a lot of 4L devices out there. But a 4L device occurs when you have a node at one end and an antinode at the other end of a tube, of a pipe. The only way that can happen is when one end is closed. When you have a pipe that's closed at one end, you can't get an antinode right there. You can only get a node. Let me show you this most simple example of a 4L device that I can come up with. I've got another tube right here, right? But this tube isn't open at one end, it's closed, right? When I go like this, I'm making the air inside resonate. And do you notice how it's a really deep sound? That's because I can make really low frequencies in this pipe. I can make really low frequencies because the wave is going to be much longer than it would be if it was open at both ends. There's a node at the bottom and an antinode at the top. This is like a tribal thing. That's it. That's it for my musical ability right there. Okay, that's all I got. Okay? When you have a device like this and you create a node at the closed end, I'm going to actually draw this on the TV so that people that are watching on the video can see it a little bit better. You end up getting a much longer pipe inside than you would if it was a 2L device. Here's a 2L device pipe. It'll go like this to get antinodes at the ends, and the rest of the wave would be like this. Right? But if you had a pipe that was the exact same length, but it was closed at one end, then if you can get a node there, then the whole wave, well, runs off my TV. I didn't give myself enough room to do it. It's a much longer wave that resonates inside that pipe, and therefore it's a much lower frequency. This is a node over here. This is an antinode right here. What's weird is the next one that would resonate inside of there isn't just like here. The next one that'll resonate looks like this. That's actually a half step over from a quarter, so that's like 3/4 of a wave. The next one will be 5/4 of the wave. The next one will be 7/4 of a wave. One thing that's really interesting about a 4L device is that you only get odd harmonics inside. You don't get the even harmonics. So this equation that I'm showing you in the notes, to find the wavelength, it would be 4L over N, but N can only be odd numbers, 1, 3, 5, 7, etc. Okay? So let me show you how you can recognize this on a FFT graph, and you'll see where the odd harmonics are basically, or the even harmonics are basically gone. Okay? One more time for an FFT graph. So in order for me to do that, I need a device where it's closed at one end. This little whistle is perfect for that. By the way, this is also a good time to just show you like the difference between a 2L device and a 4L device. Right now, this is open at this end. This is open right here. This has a name to it. I think it's called the umlaut, but I can't remember quite sure. Musical people might know what that is. But that's where the two antinodes would be. And so if I was making this a 2L pipe, it would go, right? That's the fundamental frequency that will resonate in that 2L pipe. Watch what happens when I close one end. Much lower frequency. Because now I forced a node right there, which makes a longer wave. Let's see what that looks like on the FFT graph. You ready? Pretty good, pretty good. So, how would I find the first harmonic?
The tallest first one.
This one is tallest, but generally it's always the first one. First one closest to the left, farthest to the left. Right here, bam. That's F1. F2 should be right there. It kind of is. Do you know why it kind of is? Because when I was holding this, I didn't have a perfect seal. If I had a perfect seal where no air could get out, that wouldn't be there. I would say there's like a missing second harmonic. But here's the third, and here's the fifth. Again, there's kind of a short little fourth. But the reality is a perfect 4L device only has a first, a third, and a fifth. Another great multiple choice question maybe on the final would be something like this, right? I give you two FFT graphs. One of them looks like this. That's one of the FFT graphs. The other one looks like this. And I say, which one of those is a 4L device? Is it A or B? If you're watching this on video right now, you can't hear Mr. Pinnell next door making ridiculous noises. My class is wondering why. So anyway, A or B, which one's 4L? B is, right? This is 4L. Because there should be a second harmonic right there, and there's not. It's missing. You see what I'm saying? Okay. 2L and 4L devices. Hey, I have one more quick little just simple demo that everybody who had me in class yesterday, you guys saw this, but many of you haven't seen this. I can demonstrate all of the harmonics that exist on this meter stick, or all the different kinds of devices. I'm sorry. So here's a 2L device. You see it? Nodes on my hands, an antinode in the middle, right? Here's also a 2L device. A node on my hand, antinodes on the end, right? 4L device. Node at my hand, antinode on that end. Here's a 4L device at its third harmonic. You see it? Right? Looks kind of like a little fish. I can't make the fifth. I'd have to move my hand up and down so crazy fast. I can't do that. But really, that's just a nice way of seeing all the different kind of device resonances that you can get. Cool. Any guys have any questions for me? All right.